All right, welcome back. We are ready to resume with our plenary session where we present best paper candidates. We have 4 best paper candidates, and our first one is on Polar-QUIC, and the author is here as well, Jiang Lui, and he will present his work and for us today. All right, so please welcome the speaker.
Hello, everyone. My name is Yang. I'm glad to have the opportunity to talk about, to share my work with you today. The focus of my presentation is Polar-QUIC, adaptive packet level polar coding associated QUIC in satellite networks. In this talk, I will walk you through the motivation behind this research, the challenges we face in satellite network communications, and how we propose to address them using packet-level polar code integrated QUIC protocol. So let's dive in. Here's the brief overview of what I will cover in today's presentation. Let's start by looking at the background of the satellite works and transport layer protocol. As our world becomes increasingly interconnected, satellites have grown in the principle for bridging vast distance. Despite remarkable technological advancements, we still face significant changes in satellite communication. One major change is the long propagation distance, leading to extended round-trip time. Additionally, handovers between satellites often cause packet loss, affecting the data transmission reliability. To address these issues, transport layer protocol must be resilient and adaptive. TCP will essentially face pronounced limitations due to the handshake delays and retransmission inefficiency. And to QUIC, a modern and adaptable protocol that enhances network performance using the zero RTT to establish the connection and forward error correction to enhance reliability and recover the lost packets. Okay, let's explore how FEC can significantly enhance the performance of the QUIC. FEC adds the redundancy packets to the source of the packets and allowing error correction. This enables the receiver to reconstruct missing packets, crucial for overcoming delays and data loss in satellites. Here's the system operates. At the send side, the source packets are processed by the encoding matrix to create redundancy packets. Both the source and the redundancy packets are sent over the satellite link. Packet loss is common in these transmissions, but FEC can mitigate this issue. The receiver side can use the decoding matrix to recover lost packets, such as like this packet 1 and packet 4. On the diagram below, the traditional transmission schemes experience the delays over the 1 RTT for packet loss recovery, significantly slowing the communications. But FEC eliminates these delays, enabling immediate data recovery with received redundant packets and faster the communications. The motivation of our research is driven by the limitations of the current FEC schemes in QUIC protocol, such as the XOR, the Solomon, and the random line calls. These methods try to balance the computational and complexity and the recovery capability, leading to compromise their efficiency and scalability in the complex network environments like satellite communications. The Polar code balances complexity and error correction, offering a promised FE solutions. Our study highlights the exceptional performance of the Polar codes. We learned that for near Shannon capacity, there are no complexity in encoding and decoding, ensures the high efficiency, making them ideal for 5G control channels. We propose the packet level Polar code, extending them from the physical to the transport layer. What are the challenges that the Polar code face in adapting to the QUIC? Firstly, we should reconstruct Polar code encoding and decoding modules for the transport layer to meet their unique requirements. Secondly, adapting Polar code redundancy based on the link packet loss rates. Lastly, we should modify quick retransmission packet threshold to leverage Polar code's error correction capability and minimizing false positive retransmissions. To solve the challenges, we have developed a process framework called Polar-QUIC. There is an overview of the framework's functionalities. On the Polar-QUIC sender, the key components include integration of the heuristic packet threshold-based and time-based loss detection, emulation of the loss rate using detection statistics, adaptation of the redundancy based on packet loss and loss rate and network congestion window size. At the Polar-QUIC receiver, its core component is the packet level Polar decoder to recovery lost packets, providing feedback to the sender about recovered packets. So next, to address the challenge one, we restructure the Polar code to meet the transport layer's requirements. So at the encoding stage, we restructure the packet level Polar code by leveraging the kernel matrix, kernel matrix F, and we derive the systematic encoding matrix G6, which is adaptive based on the channel conditions, such as the packet loss. And for the decoding phrase, we utilize the Gaussian elimination. Once we have received a sufficient number of the packets, we can assemble the decoding matrix using the gathered data. As soon as we have at least the key rows of the data, we began decoding. And for the challenge 2, we developed a packet loss rate elimination algorithm implemented by the sender. The sender computes the average the packet loss rate over the multiple time t. This computation provides a crucial eliminator of the packet loss rate over the entire link and have two basic functions. PR serves two purposes. The first one is to construct a Polar coding generation matrix to optimize the error correction by the accumulator PRR. The second tool is to adaptively turn the code rate to balance the bandwidth utilization and the resilience based on current network conditions. Let's continually talk about the adaptive Polar code redundancy strategy. Our algorithm takes into the estimated packet loss rate from the previous step, and you can see the congestion windows to determine the appropriate number of the redundant packets to transmit. To prevent further worsening of the congestion-related packet loss, redundancy is disabled if the congestion window is less than half the code length or can't fit the redundant packets. By considering both packet loss rate and the network congestions, we ensure that redundancy level is chosen wisely, not too high, which is wasting valuable bandwidth, nor too low, which is affecting reliability. To solve the challenges, we developed a adaptive packet rewarding series threshold adjustment strategy. The fixed on the as shown in the figure on the right, the fixed packet rewarding threshold, which is set as 3, can result in unnecessary transmission even after recovering those packets through the Polar-QUIC schemes, leading to wastage of the precious bandwidth. So I developed a heuristic algorithm to adjust the packet rewarding threshold. With the integration of the Polar-QUIC at the FEC scheme, we initially set a more aggressive packet threshold that matches the length of the FEC coding block. When loss detection is triggered by the packets, we doubled the packet threshold. But when loss detection is triggered by the time, we reduce the packet threshold by 1. Move forward after completing all the designs, building on the quick FEC framework, we have successfully integrated the Polar-QUIC into the quick protocol. Especially, we embedded the Polar-QUIC in encoding and decoding modules within the quick code base. Parallelizing this process to reduce the latency for encoding and decoding operations. The integration ensures that our Polar-QUIC framework operates seamlessly within QUIC, leveraging the robust error correction capabilities of the Polar-QUIC while maintaining high performance in test scenarios. Move forward the evaluation. For the assessment of our Polar-QUIC framework, we adopt a ratio-based matrix to measure download completion time. This ensures fair and consistent comparisons with other benchmarking programs. To replicate satellite network conditions, we set up an end-to-end simulation platform using Minilat. We use eBPF 12-box to configure packet loss rates following common satellite simulation parameters. The evaluation environment test both uniform burst loss scenarios. This approach enabled through assessment of Polar-QUIC's performance across diverse network conditions. Performance on the uniform random packets. Under the uniform packets, random packet loss scenarios with a fixed redundancy strategy, Polar-QUIC consistently outperforms other FEC integrated quicker schemes in the 0 to 5% packet loss range. Notably, Polar-QUIC has a better DCT performance than RS-QUIC, reducing the average DCT by up to 11.4%. Next, look at the adaptive redundancy strategy under the random packet loss. In the 0 to 5% packet loss range, Polar-QUIC adaptive strategy reduced DCT 30.2% compared to RS. In the 6 to 15% packet loss range, Polar-QUIC reduced DCT by about 70% to reduce against the RC-QUIC. Let's look at the evaluation performance on the burst packet loss. For the fixed redundancy, our scheme achieved up to the 5-point line reduction in average DCT compared to RCE in the burst loss conditions. As for regarding the adaptive redundancy, Polar-QUIC reduced average DCT by up to 10.9% compared to the original QUIC. It also cut performance as QUIC and RLC QUIC with reductions of up to 24.1% and 6.1.6%. In conclusion, let me summarize the main contribution of our work and outline the future direction. Firstly, we developed and implemented the first packet level polar encoder and decoder for QUIC. Secondly, we designed a adaptive FEZ scheme based on packet loss rate and the congestion window, improving the robust and the efficiency. Thirdly, we introduced the adaptive packet threshold scheme to reduce force triggered in QUIC loss detection. Lastly, we achieved a significant reduction in average DCT. Move forward, we plan to compile Polar-QUIC with TCP variants in high latency network. The second is to conduct a real-world tool deployment and testing to perform a theoretical analysis and the shallow vibrations. These steps will ensure that our solutions are not only theoretically sound but also practically viable. That's all. Thank you for your attention. I'm happy to take any question you may have.
All right. All right. So are there any questions? Oh yeah, awesome.
Can you go, I think it's on slide 7. It's at the beginning of the book. So what's the feedback you, so I didn't get how you detect the losses based on the feedback you receive, because right now you're just returning acknowledgements, which are after you recover the packets. So how do you know that you've lost the packets, but that has been recovered?
We do the loss animation at the sender side. They use they use the packet threshold based and the time based loss detection in the QUIC to animate the packet loss. For example, if the packet is received the ACK, the receiver send the ACK to the receiver send the ACK to the sender and to acknowledgement the packet is received. But if the ACK is delayed 1.125 the RTT, the sender determined the packet is lost to counter the loss rate.
All right, further questions?
Thank you. Thank you for the talk. So you, if I get it right, you develop an adaptive forward error correction mechanism, right?
Yeah.
And in the evaluation, you parameterized your failure models for uniform losses and burst losses.
Yeah.
But did you also vary them? So varying the parameterization because you have some adaptive thing. And if you constantly evaluate without varying loss rates, then you can't really evaluate the adaptivity. And if I got it right, one of the core contributions of your work is adaptivity. So can you comment on this?
So in the uniform and the burst loss detection, we do the test separately. So I don't do this test.
Are you happy?
Not really got it, because if you can go to the slide where you have the table where you parameterize the error model.
Page 1.
So the evaluation setup where you have this table with the parameters of your evaluation. So there's a far end where you show the evaluation results. On the first slide, you had a table that's also in the paper. Okay. At the far end, in the evaluation. Yeah, this one.
Oh.
So if you look at this, if you look at this parameterization, is it varying? Because if you have a uniform randomness, of course, it stays the same. But for the burst losses, what kind of loss rate do you result in? And if you look over certain time windows, is it really on different levels based on this parameterization so that you can evaluate your adaptivity?
Yeah. We just use milliliter to simulate this loss rate. So in the uniform, during a long time it make the uniform, but the short time is flattening.
Okay, we can take the rest.
All right. We have time for one final quick question. Quick one.
Quick question for quick protocol. So I wonder about the implementation, if the code is available, publicly available. Number one. Number two is how did you implement this? Is this at the physical layer or the transport layer? And then after the implementation, how did you integrate it to Mininet?
Yeah. I extend we use the the Polar-QUIC encoding matrix to encode the packets. This is the different of the physical now. It encoded the bit, but in the transport layer, we encode the packets. This is the difference. We implemented this way to extend the Polar-QUIC from the physical to the transport layer.
Do you have the code available?
Yeah, we use the quick go code base to implement our solutions.
All right. With respect to time, let's thank the speaker again and move on.